I have to say that John is being very brave because he's actually changed the title, because I was going to say it doesn't use the word Bodger's Guide, but I'm delighted that he could change the title to include the update of Bodger's Guide. So, John, I think you're ready. You've tied yourself in knots. So
I'm really tied in knots. Hang on, I'll be with you in a second.
Great. Still missing one. Oh, you got it. Thanks very much.
Right.
Right.
Are you set, or are
yes.
you okay with that? John, the floor's yours.
Okay. Good afternoon. Some of you might have seen something similar to this. It's a bit of a recycle thing, but somebody asked us to talk about biasing of amplifiers and sort of doing things with RF power amplifiers. So what I'm going to do is just run through some of the basics, and I should point out first of all that I'm not really a professional RF designer. I've dabbled, like most of the things I did in my life. I dabble and bodge, hence the title, The Bodger's Guide to Amplifiers. But hopefully we can get something interesting for you to talk about. I'm going to talk about two things. I'm going to talk about biasing and matching amplifiers so that they produce power from a device. And I'm going to talk really about LDMOS, GaN and GasFETs. So just a quick introduction. You've all heard of LDMOS devices. You've probably all got an LDMOS PA. I'm just going to change size because that's lighting and that's shining in my eyes. LDMOS is a type of MOSFET, but it's a power MOSFET. And when I was doing RF design professionally many years ago, they didn't have these. And one of the problems was always getting a good ground onto the emitter of your RF device. But the great thing about LDMOS is that the source, the bit that goes onto the ground, is right at the bottom. So it does make them very good for getting a good ground on the bottom of your device. And it's cheap to make, it's very good, and you can generate lots and lots of power. You can generate kilowatts of power at VHF with this stuff. There's a rather newer version of FETs, which is a gallium nitride device. It's actually gallium nitride on silicon, and it's a higher frequency device. It's a more modern device, but again, you can get things like, sorry, I'm just getting used to the buttons at the moment. I've lost my cursor. But you can get something like 10 watt devices at 40 gigahertz in this technology now. So it's quite interesting stuff. Again, it's very simple to bias, just needs a simple positive gate, and you don't need too much of clever bias circuiting on it. So that's the two main things I'm going to talk about. I'm also going to talk about GasFETs, which are slightly older, but you'll still come across them, especially in surplus. So you've got a choice as an amateur. You can buy stuff, and it can be quite expensive. You can grow your own from kits, you can design your own stuff, or you can modify surplus. Quite frankly, modifying surplus is the good thing to do, because you can get some very nice amplifiers and very nice devices around in the surplus market for very little price. So I'm going to look at the sort of last two really, rather than buy things. Anybody can buy stuff. As I always say to the EMEers who've got huge stations, I say any fool can do AME with enough money and a big enough dish, and the same applies to amplifiers. So let's go through back to real basics on amplifier design, and this is not a high-level design guide. You've got to do two things. You've got to first of all set the DC conditions of the amplifier, bias the thing up so that it works under its whole range of power level, and you've got to match the device to the output stage and to the source. So that bottom diagram there is a block diagram of a single stage power amplifier. You've got a device in the middle, you've got a bias supply which supplies VDD, the drain voltage, and you've got VGG is the gate voltage. The drain voltage is the high current one, and the gate voltage is the thing that sets the bias level. So once you've biased your device up, it then needs to see certain impedances to work properly. And you've got 50 ohm loads and sources mainly. So what you have to do is you have to match the input device so that when the output is matched, and that's quite important, the input match looks like 50 ohms, and the device is looking at the impedance it wants to look at to deliver maximum power. So it's two things. The input matching is making the amplifier look like 50 ohms from your source, and the output matching is making your device look at the right impedance to produce maximum power. So that's very basic start. First of all, biasing. Both LD, MOS and GAN are enhancement mode FETs. What that means is they're designed to be off when there's no gate voltage applied. And when the gate voltage is pulled to the drain voltage, they switch on. And the amount of gate voltage you apply depends on how much current they take. The older gas FETs are known as depletion mode. They're the other way around. They're designed to be on when the gate voltage applied is 0, and off when the gate is more positive than the source. So some of you might even see that and think, that's interesting. They're on when there's no gate voltage, and on means effectively a short circuit between drain and ground. So that's the two types. LD, MOS and GAN are enhancement mode. They need a positive bias to turn them on, and gas FETs are depletion mode, which need a positive bias to turn them off. And that's the basic difference between the two.
John, do you mean a positive bias to turn them off? Or do you mean a negative bias to turn them off?
When the gate voltage applied is 0, they're off.
No, for depletion mode.
Sorry, let me start again. For depletion mode FETs, if they have 0 gate voltage, they are on.
Yep. And
With enhancement mode, when they have 0 voltage, they're off.
yes, but a depletion mode, don't you need negative gate voltage to turn it off?
Yes, sorry.
Right. Okay.
It has to be more positive than the source. Hey?
No, the gate needs to be more negative than
Oh.
the source.
Sorry. Yeah, okay. Sorry, my apologies. But the important point to get out of this is when they've got 0 volts, they're on. And that becomes quite important later on. I'm sorry, I'll correct that. Right. Let's first of all look at how you actually set up the bias on these things. As I've said earlier on, the gate voltage controls the quiescent drain current. The quiescent drain current is how much drain current it's taking when there's no drive. And the device depends on having a certain level of this thing IDQ for the best operation. Basically so that the supply can swing over the required range. If you buy something in Class A, that means the thing is set at half the rail. Anything less than half rail we normally refer to as Class AB. But there's Class B, there's lots and lots of other classes which I'm not even going to go into. But the basic thing is, what you normally do with LD MOS is you bias it in Class AB. And each transistor in an amplifier will require a unique gate voltage to give you the required drain current. And they're not necessarily exactly the same. So if you've got two devices, you probably need two separate bias supplies. Okay? Because they won't be exactly the same. And it's quite simple to set up the IDQ of the device. You actually power up the amplifier, put the drain voltage on. measure the drain current with no RF drive, and then apply gate voltage, a positive gate voltage, starting at 0, creep it up, slowly increase the gate current while you're looking at the drain current. And first of all, nothing will happen until you hit about 2.5 volts, and then suddenly you'll start to draw drain current. When you get to this gate source threshold voltage, this VGS-TH, if you keep on going, you'll put so much gate voltage on it, the thing will draw lots and lots of current and destroy itself. So you have to be very, very careful, and you have to limit your gate supply so that you can't do that. If your gate supply can't go much above 3.5 volts on most devices, you won't do that. But if you put a 5 volt supply on it and do that, which you can do with some of my amplifier designs, sorry, it is possible to blow them up. So, very near 0 with no gate voltage. So you then creep the thing up, and the data sheet will have a value of quiescent current that's optimum for a particular output power and operating condition. And you can set that. It needs to be regulated, but the good thing about this, unlike old-fashioned bipolar transistors, is you don't have to, it doesn't vary much with temperature. What you'll find is you set the drain current to say 50 milliamps when it's cold, come back 10 minutes later once it's warmed up and it's probably 60 or 70 milliamps. But what I normally do when I'm specifying this, because most people will turn them on from cold, is you set the cold gate current and you just live with that 10-20% increase, because it's not really critical. So it's quite a simple thing to set up the bias. There are lots of these amplifiers you can get in surplus will have all sorts of complicated bias circuits and switching to turn them off and vary the current. The best thing to do is, if you've got an amplifier, that is just disconnect everything else, get a 3.3 volt regulator and a pot, and just bias the devices separately. Unless, of course, you have something called a Doherty amp. Doherty amp is 2 devices. One's biased in class A, B, and the other one's not. And there's a very clever bit of matching circuitry that enables you to actually improve the efficiency by running one device in one mode and one in the other. But I'm not going to go into that. But if you come across with a device like that, you need to think a little more carefully about fiddling around with the bias. Right, moving on to gas FETs. The reason I talked about the drain voltage, the gate voltage being 0, if you take a gas FET, a depletion mode gas FET, and you put 5 volts on the supply, and you forget to put the gate voltage on, it will die. Bang. So you can have a £100 gas FET, you can forget to switch the bias on, and it'll blow. You'll have a very expensive fuse. So you have to design a bias circuit that knows whether there's drain voltage. And there's lots of circuits around. Charlie Suckle in G4BAO has done a really nice circuit, which you can find anywhere on the internet, which stops you applying the drain voltage before the gate voltage. But if you do, or his circuit fails, you're buying a new gas FET. So, what you've got to do to bias up a gas FET is start with 0 drain voltage and apply the gate voltage first. Once you've applied the gate voltage, you can slowly decrease the gate voltage until you start to draw current. So it's completely the reverse from doing GAN and LDMOS. So then you've got to set the bias by actually turning the gate voltage down. Okay, and again, once the gate drain current starts to flow, and this thing comes on very quickly, and you can go from microamps to amps with a very small change in voltage, so you have to be careful. So again, you have to regulate that voltage. But again, you'll find most of the ex-commercial gas FET amps you buy have got power supplies that automatically generate the gate voltage from the drain voltage, and it's possible to actually delay the application of the drain voltage by a few milliseconds, because that's all it needs. So it's a slightly different thing with old-fashioned gas FETs. So that's biasing. So we've got our device. It's on the board. It's heat sinked. It's biased up to correct thing. The next thing you've got to do is make it deliver power. Now, RF power devices are very low impedance devices. They're something in the terms of an ohm or less, unless they're internally matched. You can buy devices now that are internally matched, and they're just 50 ohms in and out. And with these devices, you bias them up, plug a source and a load on, and off you go. But what you've got to do, once you've got the thing biased up, is you have to match the input and the output. And if you look on a data sheet, it will give you data on what the impedance of the device is and what impedance it needs to look at to deliver maximum power. And then it's a case of designing matching networks that will transform those impedances over the bandwidth you want. And these can be anything from one microstrip line and a capacitor to multi-stage wideband matching networks. One of the things you have to do, one of the things you need to be careful of, you've got to make sure the impedance matching doesn't make the amplifier go unstable at other frequencies, because it's possible to present a device with an impedance that makes it go unstable, and once again, what happens usually then is you end up with a dead device. So, bias and impedance matching. So, we just need data sheets, right? Yeah. No. That's fine if you've got data for the band you want. Unfortunately, as amateurs, we're stuck with, especially LD MOS, we're stuck with stuff that's designed for cellular radio. There are more wideband devices out, but the sort of surplus you will come across will be 900 megs, it'll be 1.8 gigs, it'll be 2.1, it'll be 2.3. So for 13 sems you can get away with the amplifier as it works. But you've got a problem if you've only got data for 900 megs and you know the device is wideband. If you take my now very ancient 35 watt PA I did, that's a device that's good to a gig, but it does work at 1296. But I only had impedance data for 900 megs. So, what do? We're stuck. Nah, no we're not. We don't usually have the technology to measure device impedances because it requires jigs and a network analyzer and all sorts of clever stuff. So rather than go out and buy an expensive network analyzer, I've invented this thing I call the Bodger subroutine. And it's applicable to new designs, or if you don't have data, or if you're retuning surplus. Sounds very impressive, but it's not. It's make an intelligent stab at what you think might work, and then cut, try, optimize until it's working satisfactorily. I know it's horrible, and I'm so glad Charlie isn't here, because he would have his head in his hands at this point. But he does work for one of the big semiconductor manufacturers. But that is a way of doing things, and you can actually, if you really have no impedance data to do this design, you can actually make an intelligent guess. So I'm going to talk in the next couple of sessions about how do we make this intelligence guess. Because the first thing we have to do is get the device to look at the right impedance to deliver maximum power. And what you need to use this Bodger subroutine is a pair of cheap vernier calipers to measure things, a roll of adhesive copper tape, a sharp scalpel, some plastic insulation tape, a Smith chart program, and I can see your eyes glazing over already at the mention of Smith charts. There's a program called AppCAD, which is a freebie RF design program, and if you've got 50 quid to spare, a cheap mini VNA. Since these came out, this has made this bodging process a little bit easier, and I'm going to talk about a technique that I have tried that does work reasonably well. And of course, you need something to bodge. These were out of a 900. These were out of a 900 meg amplifier, and I actually got these working on 1296 with a lot of bodging. They were made by Andrew Corporation, who were famous for connectors and antennas and things. So, right, how do we do output matching without a data sheet? It's actually, especially at VHF, it's remarkably simple. Gets a bit more complicated at UHF, but what I'm talking about here is getting a first stab of what might work, and then you can get your power meter out and your copper tape and tab stuff. That's what an LDMOS, I keep pressing the wrong button. That's what an LDMOS device looks like. It's a current source with a drain source resistance across it, a drain source capacitance, then a gate source resistance and a series gate drain capacitance. And these things, these two circuits here, are the interconnecting wires inside the chip. These are the bond wires, and that's the bond wires to the source. So that's the equivalent circuit. If you look on PSpice, you'll see that circuit as a bog standard circuit. So if you provide a signal into a device, what you're trying to do is to get the drain voltage to swing from your supply down to the drain voltage when the device is on. So there's a swing of between VDD, that's your power supply, and the VDD on of the device, which is a few volts. So to a first approximation, don't forget I'm doing quick and dirty here, it's approximately 0 to the supply. And if we assume the waveform sinusoidal, and it rarely is, but it's a close approximation, what you end up then is a sinusoidal voltage across your load, going from 0 to VDD, so your output power is that. Standard basic Ohm's law. It's VDD squared over 2RL. That's your output power. And if you want to maximize that, what that means is, so to deliver that power, the device needs to see that equation rearranged, which is it needs to see a load resistance equal to VDD squared over twice the output power you want. Simple, basic DC, AC circuit theory. But there's a capacitor in parallel with that, right? So what we need to do is resonate that out. So you effectively need to conjugate match it. So you need to basically put a parallel inductance across that, across CDS, to resonate it, and then all your output power will be there. So we've already got the resistive part of our load impedance that it needs to see. We have in fact got our outward network devices. It needs to see a resistance of that in parallel with the conjugate of CGS, which means the inductive equivalent of that. So that is what the device needs to look at to deliver maximum power. Now, we don't like parallel things, so if you convert that to series, R plus or minus JX, which is resistance and inductive reactance or capacitive reactance if it's minus, you could do that using maths, or you can do it on a Smith chart. A Smith chart will enable you to go straight from one parallel to serial. So, just to take an example, a single-ended VHF device, which is a 300 watt 50 volt device. If you do the sums on that at 300 watts out, you end up with 4.16 ohms in parallel with 120 puff. You've got to make your 50 ohm antenna stroke load look like that. If you convert that to series and do the conjugate, you end up with a load impedance of 3.2 plus 1.76 ohms. So you can see they're quite low impedances. And if you look up the data sheet, because this is a device I have the data sheet for, it's pretty close, yeah? And that's just from basic AC audio amplifier theory. You can get very, very close. So, is that close enough now? Sorry, I'm going to have to get the Smith chart out. Let's just try designing an impedance matching circuit for those two things and see how different it is. Right, I bet you know. Have you seen a double Smith chart like that? It's called an emittance chart. That allows you to directly convert from parallel to serial. It allows you to plot complex impedances. All these numbers here, these are all normalized resistance. So 50. So you've got 50 ohms through the center of the chart. So the center of the chart is 50 plus J0. This is very high impedance, and that's very low impedance. More of this in a minute. There's other circles you can plot on that. A circle centered on the center, any point on that line has got the same VSWR. Right? And the VSWR of 1 is a dot in the middle. The other sets of circles, you've got constant resistance. So anywhere on that red circle has the same resistance. Anywhere on that circle has the inverse of resistance, G. Okay? You know it gets very complicated when you get there, but if you want to plot something, you actually plot what's known as a normalized impedance. So it's the actual impedance divided by 50 ohms or whatever your impedance is. So if I wanted to plot 10 plus J4 on there, that would go there. That's 10 plus J4 goes on that point. It's positive, it's inductive. So the top half of the chart are all inductances, the bottom half of the chart are capacitances. So 10 minus J4 would be in the same place but in the bottom of the chart. Okay, let's swiftly go beyond this. Let's go back to my output matching thing. If we start off in the centre is where we want to be, right? If we then move round that circle, that's shunt capacitance. Anything on that circuit is this shunt capacitance. So we go from 50, that movement is shunt capacitance, and that one, which is on one of the other circles, is series inductance. Okay, so what we actually do is we end up there at that point. That's our 2.7 plus J2. And if you look what falls out of this magic Smith chart program, that says that needs an inductance of 12.4 nanohenries and a capacitance of 76 picofarads. That will match our data sheet value of impedance. If you put our estimated one and do the same thing, you end up with 12.3 and 70.7. So it's within 10% of your matching components that you need are within 10% of what the datasheet had. So if you didn't have the datasheet, you can get to a point where you can start fiddling around and tweaking values and putting variable capacitances in until you've matched it. And the only thing we've used in that is a Smith chart to do the matching calculations, which is another talk altogether. And we've used basic amplifier theory. So,
John, 5 minutes.
oh, crikey. Okay. Right. Input matching. We've got our output stuff matched. They're slightly more difficult because there's no obvious way that you can, without measuring the impedance, but there's a really nice cheat. If you've already designed the output network roughly, build it, stick your device in there, and just put a straight 50 ohm line into your device input. Right? Bias it up and just measure the whole input impedance of that thing, line, device, output matching network load, with your mini VNA, your 50 quid mini VNA, and that'll give you a point on a Smith chart. Now that point on the Smith chart is not the device impedance, it's the device impedance plus the transformation of that 50 ohm line. And if you measure that 50 ohm line, you can use a Smith chart to go backwards and come up to the device impedance. A reasonable estimate of the device impedance. Not a perfect one, but I have done this and it works. Just put an SMA connector on it with a piece of 50 ohm line that you know its length, measure it on the VNA, use a Smith chart program to work out what the device is presenting to that line, and you've got your input match. Then you can take your estimated input match and you can use a Smith chart to design a matching network to do that. And most of the UHF stuff, if you look at most UHF and SHF amps, they have a fat input line, and that's about 12 ohms. And you can do this on the Smith chart, plot your impedance, take a 12 ohm transmission line, and then just have a shunt capacitance. And then you power it up, see how much power you get, and tweak it. I told you it was the Bodger's guide, but it is possible, and you can get some decent designs, and you can modify stuff. So, a few do's and don'ts to impedance matching in general. Try and avoid shunt capacitors because they tend to be lossy. Watch the capacitors out rating and current. 100 watts at 50 ohms is 1.4 amps flowing through your capacitor. Try and avoid trimmers unless you're setting up, and then measure your trimmer and put a fixed capacitor in. Recycle as much of the original amplifier as you can, the bias circuit, the PCB. If it's already got a fat connecting line, try and use that. Don't bother trying to do internally matched devices that are not matched for your frequency. Watch the gate and bias voltages, and don't use FR4 at UHF because it cooks, unless it's proper microwave FR4, and the stuff you get from Amazon isn't. Very quickly moving on to mounting devices because I'm running out of time. You have three choices: bolt it down, clamp it down, and solder it down. Soldering's the best because if you bolt stuff down, look what happens. That's pressure sensitive tape. Oops. The red bits are where you've got the best contact, and that's what happens when you bolt transistors down. They do that. So clamp them. If you're not going to solder them, clamp them. Right? That's straight from the Freescale application note. Use a copper heat spreader. Don't use interface material when you're clamping, as long as the heat spreader's flat enough. And that means a professionally milled heatsink. Solder it, if you can, most devices you can solder, especially if you use low melting point solder, which you can get, or use silver grease. And you can also buy this stuff called T-Gon 805, which is graphite sheet, and if your heat sink's not quite perfect, because it's conductive and it's heat conductive. So get the heat away quickly. Always use a copper heat spreader. Try and avoid shunt capacitors. Then the last thing, there are some very simple things you can do without much test gear. And I've designed especially VHF amplifiers using this technique. So give it a go, especially if you've got lots of cheap surplus devices. But they're quite difficult to blow up. Just a few acknowledgements. This guy with the wonderful name taught me RF design. He went on to work with, I don't know whether you guys know Al Katz, the EME legend from, is it Princeton? But Sud went on to work in the States for RCA and all sorts of people as an RF designer. But he taught me all my early days. Back in the days when they didn't have CAD, we had Smith charts and pencils. And I've had a lot of help over the years from Chris G4DGU and Charlie. They all seem happy to put me straight. But okay, that's it. Unless you have any questions, I hope that's been interesting.
Thank you, John. Any questions? One, none. Any questions online?
Yes, I do have one. Got a question from Gareth, G4XAT.
Oh, have you got my coax switch? Is it?
It isn't that, but other than the budging method, is there any mileage in extrapolating manufacturers' data graphs that don't quite cover your desired frequency?
Yes, I've actually, it's not perfect, and I can see Dave is cringing over there, but it is possible as long as you don't try and go too far, because what they normally plot is 3 or 4 frequencies. Now I've never got a straight answer from a real RF designer, is just how do they go? Do they suddenly start doing that? But I have actually, that's how I got close to the impedances for that 35 watt amp. I extrapolated and I really mixed. But as I said, this is not professional RF design. This is, can I make it work? But yes, there is some mileage as long as you don't go too far.
Yeah, I mean, he's using a BLF 888A, and his experience is that even though it's only spec 500 meg to 1 gig, he's got it happening sort of quite well at 23 centimetres, and maybe even at 2 metres. So.
Yeah. Well, as I say, that device I used in my 35 watt amp is normally a 1 gig device, but it worked perfectly well at 1296.
Okay, thank you very much. We'll break there. We are due to restart at 2. We'll stick with that, so we'll reduce the break from 45 minutes to 15 minutes. But thank you very much, John, and thank you to all the speakers today.